Let's now turn our attention to triple integrals. These are a generalization of the idea of a double integral. So let me just remind you, if we have a single integral, that is the definite integral on some interval, we're integrating x's going from a to b of a function of a single variable. The definition of this involved a Riemann sum. And the answer we get out of this, we can interpret as area under the curve. There are other meanings of this integral. For example, we saw that we can have mass or other applications. If we look at a double integral over a region, this is now a function of two variables with respect to area. The definition of this involved a double Riemann sum. And again, rather than thinking this of area, the first we integrated with respect to length and we get area. The double integral we integrate with respect to area and we get volume. Or as we saw, we had other applications including mass, moments, and so on. If we look at a triple integral, this is now the integral of a function of three variables with respect to volume. This is defined in terms of a triple Riemann sum. And now this, we no longer have a geometric idea on what this is. It's not volume anymore because the second dimensional integral was volume. This is going to give you some four-dimensional measurement. So as far as a geometric interpretation, we really can't extend this any further, although the other applications still hold. We can still interpret this as a mass or other applications like moments and so on. But we don't really have a good idea of what this four-dimensional volume is. We can't really visualize that. So we can't think of this in terms of area under curve or volume beneath the surface anymore. Now this triple Riemann sum, the definition, and we're just going to write this out informally. The definition is we're taking the limit as the size of the partition heads to 0. And now we're summing up the volumes, well not volumes, the hypervolumes of a bunch of boxes. The boxes run in the x direction, they run in the y direction, they run in the z direction. For each box, we're going to take its sort of fourth dimensional height. So we pick a sample point, an x, y, z sample point in each one of those boxes, and we multiply by the volume of that box. Now, the volume of a box is given by length times width times height. And so this is going to we send the size of the partition to 0. That is the volume of the largest box heads to 0, and this gives us, this is the definition of this triple integral over a region f of x, y, z with respect to volume. Luckily, Fubini's theorem in 3 dimensions gives us a way to rewrite this triple integral of this function f of x, y, z with respect to volume as a threefold iterated integral. So we're rewriting a triple integral as an iterated integral. And the triple integral, first we integrate with respect to x on the outside. The x's have constant limits of integration. Then we integrate with respect to y. Now the limits on y can depend on whatever is outer to the y integral. So these limits can depend on x. Then we integrate with respect to z, and our limits of integration for z can depend on anything outer from the z's perspective. So these limits can depend on x and y. The top limit can depend on x and y. And then the integrand is still the same. So that function stays as is. So this is Fubini's theorem letting us rewrite a triple integral as a threefold iterated integral. Let's look at an example of this. Let's look at mass, because we can't really look at hypervolume and make any meaningful sense of that. So mass is defined as the triple integral over the region of some density function. Let's suppose that our density function is 12x y cubed over z squared, and we're finding the mass of, so this is the density, and the region is given by the part of the surface, the region between z goes from 1 to xy, let's not do that. Let's do the other way around. Let's say from xy to z equals 1 in the first octant. So if we just get a rough sketch on what this means. So if we look at this, we're going to look at a two-dimensional cross-section of this region right here. So we've got the z-axis up here, and we've got the xy plane playing the role of the x-axis. So we're running from z equals 1, that's our upper limit of integration, to z equals x times y. So x times y is going to sort of run up along this direction right here. So we've got this region in here, schematically anyway. So I can see that these are running from z equals 0 to z equals 1. Although z equals 1, that looks like it has a bigger shadow. So let's look at the shadow of this thing in the xy plane. So this is x, this is y. Now we're in the first octant, so we don't need to worry about the negative values for x and y. Now x and y, if z equals 1, which is sort of the extreme point on here, if we plug z equals 1 into this function, we get xy equals 1. So now xy equals 1, if we solve this for y, this gives us y equals 1 over x. It's this hyperbola over here. Now we've got to figure out, are we inside or are we outside? If you take any point in the region here, the farthest right we can get is xy equals 1. So that's the largest value for xy that we can get is 1. We can get lots of smaller values. So we can get everything that's in this section of our curve, on this side. So based on that, that'll give us our limits of integration. So that says our mass is now the integral. Now the x values, it looks like the x's start out at x equals 0 and they run all the way out. There is no right-hand endpoint, so they're going from 0 to infinity. So this is going to be an improper integral. If we then fix an x, do this in a different color. Let's say we fix an x value. If we look at the range on the y's run from this bottom curve. They run from y equals 0 up to the top curve. And the top curve we just identified to be y equals 1 over x. Okay, those are the outer two integrals. Next up, we're going to look at the z's. Now the z's run from the bottom curve, which is z equals xy, to the top curve, which is z equals 1. We have our limits down. Now we're going to plug in our density function. So this gives us 12x y cubed over z squared with respect to z, then with respect to y, finally with respect to x. So now we have the setup on this triple integral done. Now we're going to start integrating one variable at a time. So the outer one can sit. We can leave that integral from 0 to infinity. The y integral also we can leave from 0 to 1 over x. Now the inside one, we're going to integrate this with respect to z. So think of this like z to the negative 2. So just sort of off to the side, think of this as the integral of 12x y cubed z to the minus 2. We're going to do the power rule. So we're going to increase the power to negative 1, divide by negative 1. That gives us minus 12x y cubed z to the negative 1. And we're evaluating this from xy to 1. That took care of the z integral. Next we're going to integrate with respect to y, and then with respect to x. So that's our first step, our first inner integral. So we'll write down the next part. And the next step we're going to do is simplify the inside. We're actually going to evaluate here. If we plug our top limit in, if you plug in z equals 1, we get negative 12xy cubed. Minus, now we're going to plug our lower limit in. We plug this in here, we're actually going to have some cancellation. We're going to get 12y squared dy dx. Okay, so we plug the xy in. The x to the negative 1 cancel with this x. The y to the minus 1 cancel with one of these y's, leaving us with the y squared. This negative here canceled with the subtraction from the integral to give us a positive sign. So we've done the first integral. Now we'll integrate this with respect to y, because that's our next integral up. So the x integral can just sit. We integrate this with respect to y. Now we're going to do the power rule in each piece. So if we integrate this, we're going to get a y to the 4th over 4. So this gives us negative 3xy to the 4th. We integrate this with respect to y. We're going to get y cubed over 3. so 4y cubed, evaluated from 0 to 1 over x dx. Okay, so now our next step is to simplify the inside. So we're going to plug 1 over x in for all those y's. We're going to leave the outer integral as is. This gives us negative 3. Now if we plug this 1 over x in here, let me actually write this out. 1 over x to the 4th plus 4 1 over x to the 3rd dx. We plug 0 in for the y's and everything zeroes out, so there's nothing to worry about there. And then this we can simplify. We can write this as the integral from 0 to infinity of negative 3 over x cubed, because those 4 x's those canceled with the x here, and over on this side we've got 4 over x cubed dx. Might as well go one more step to just to algebraically simplify this a little bit. Integral from 0 to infinity of 1 over x cubed dx. Okay, now this is improper actually for two different reasons. We have an infinity for one of our limits. So it's improper due to this infinity in here. It's also improper because the integrand has an infinite discontinuity at x equals 0. So we've got to be careful for both of those reasons. So we're going to split this apart into two separate integrals. The integral from 0 to 1 of 1 over x cubed dx plus the integral of 1 over x cubed from 1 to infinity dx. Okay, so now each of these integrals we can do by the power rule. Because again, think of this like x to the negative 3. So we just copy that over the next page. So we've got the integral from 0 to 1 of x to the minus 3 dx plus the integral from 1 to infinity x to the minus 3 dx. So now we do the power rule on each of these pieces. So the first one is going to give us x to the negative 2 over negative 2 from 0 to 1. And now 0 we've got to be careful on, because that's actually a limit, because we've got this improper integral. And then the second integral is also negative 1/2 x to the negative 2, now from 1 to infinity. Okay, evaluating the first integral, we plug the 1 in. We're getting negative 1/2 minus negative 1 over 2 times, now this x to the negative 2 gives us this 0 in the denominator. So we're going to come back to that in a second. Let me just write down the second integral. This gives us negative 1/2. Let me make that fraction bar a little bigger. Negative 1 over 2, and now we have infinity minus negative 1/2 times 1 to the negative 2. Now if we look at some of these pieces on here, this first one is giving us negative 1/2 plus, we have a number over 0, so this is going off to infinity. Here we have a number over infinity, this is going to 0. And over here, 1 to any power is 1, so those cancel to give me plus 1/2. So everything cancels. Not that it matters because we have this infinity in here. So now that means that this integral diverges, but we were asked to find the mass. So we can actually interpret this as, yes, the integral diverges, but the mass is infinite. So that gives us a little bit more information than just, I can't make sense of the integral. It tells us the integral sort of blew up, but it gave us sort of a sense of how big it was, that the mass of this thing is infinite. So that's the idea of triple integral, and we'll see many more applications and problems based on it.